Hi, and welcome to the Lost Landscape. Today we're going to really understand cross-entropy, the loss function behind almost every AI model, in plain English, with no scary math. This single number is the reason ChatGPT can finish your sentences, and the reason your phone can tell a cat from a dog. It's called cross-entropy, and to really understand it, you only need two words that almost everyone mixes up: probability and likelihood. So let's build the whole idea from zero, one small step at a time, in plain English. Let's start with the confusion almost everyone has. Probability and likelihood use the same numbers, but they ask opposite questions. Probability starts with a fixed model and asks, how likely is some outcome? For example, a fair coin has a 50% chance of landing heads. The model is fixed, the outcome is unknown. Likelihood flips this around. Now the outcome has already happened, it is fixed, and we ask, how well does a model explain what we saw? So probability reasons forward, from model to data. Likelihood reasons backward, from data to model. Same formula, opposite direction. Hold on to that one idea because everything else is built on top of it. Now let's watch a model actually make a guess. Say we show a neural network a picture, and it must choose between cat, dog, or bird. Deep inside, the network does not output probabilities. It outputs raw scores called logits. Here they are: 2.0, 1.0, and minus 1.0. These can be any number, positive or negative, and they do not add up to anything neat. To turn them into probabilities, we push them through a function called Softmax. Softmax does two things. It makes every number positive, and it makes them all add up to 1. Out come real probabilities: 71% cat, 26% dog, 3% bird. So the chain is logits, then softmax, then probabilities. That is how almost every classifier speaks. Now suppose the true answer is cat. Here is the key question of this whole video. How much probability did the model give to what actually happened? The correct answer was cat, and the model gave cat 71%. That single number is the likelihood. Higher is better. Let's compare two models. Model A gives cat 80%. Model B gives cat just 10%. Since the real answer is cat, Model A explains reality far better. That is all likelihood measures, the probability your model assigned to the thing that really occurred. So if likelihood tells us how well a model explains reality, then training becomes obvious. We just tune the model until reality becomes as probable as possible. A model has thousands or even billions of internal knobs called parameters. We turn those knobs and watch the probability of the correct answer. One setting gives cat 20%. A better setting gives 60. The best gives 90. We keep the setting that makes the correct answers most probable. That idea has a name: maximum likelihood estimation. In plain words, change the model until the truth looks likely. But real training is never one example. It's thousands. So how do we score a model on the whole data set at once? We multiply. Say the model gives the correct answers these three probabilities: 0.8, 0.7, and 0.9. For all three to be right together, we need the first and the second and the third. And when independent events must all happen together, we multiply their probabilities. 8/10 times 7/10 times 9/10 gives about 0.5. So why not just add them? Because adding gives 2.4, and no probability can ever be bigger than 1. Adding is for or, multiplying is for and we need every example right together, so we multiply. Now here is a very practical problem. With thousands of examples, we are multiplying thousands of numbers, each one smaller than 1. And multiplying small numbers gives an incredibly tiny result. Something like 0.000, on and on. Computers simply cannot hold numbers that small without breaking. So we use a beautiful trick. We take the logarithm. The log has one magic property. The log of things multiplied together equals the log of each of them, added up. So multiplication turns into addition. Instead of multiplying 1,000 tiny probabilities, we add 1,000 manageable numbers. Same ranking of models, but now it is stable and fast. This is called the log likelihood. You might worry, doesn't taking the log change the answer? It doesn't. The log preserves order. If one number is bigger than another, then its log is also bigger. So the model that had the highest likelihood still has the highest log likelihood. We have not changed which model wins. We have only made the math easier to compute. There is one last mismatch to fix. Maximum likelihood says maximize, but training algorithms are built to minimize a loss, to roll downhill. The fix is delightfully simple. Flip the sign, put a minus in front of the log. Likelihood, and now maximizing goodness becomes minimizing a loss. This is the negative log likelihood. Watch how it behaves. If the model gives the correct answer 90%, the loss is small, about 0.1. If it gives the correct answer just 10%, the loss jumps to 2.3. Good predictions, tiny loss. Bad predictions, big loss. Exactly what a loss function should do. And look at how sharply it punishes being confidently wrong. When the correct answer gets 99%, the loss is almost nothing. At 50%, it's about 0.7. At 10%, over 2. At 1%, above 4.6. The curve explodes as the probability of the truth heads towards 0. In other words, the model is punished the most when it is confidently, badly wrong. And that is exactly what forces it to never completely rule out the right answer. So where does cross-entropy come in? Cross-entropy compares two things: the true distribution and the model's predicted distribution. For cat versus dog, the truth is simple. Cat is 100%, dog is 0. We write that as 1. 0. The model predicted 80% cat, 20% dog. Cross-entropy multiplies each truth value by the log of the predicted probability and negates the total. But the dog term is multiplied by 0, so it simply vanishes. All that survives is minus the log of 0.8, and that is exactly the negative log likelihood we already had. So for ordinary classification, cross-entropy and negative log likelihood are the very same number, just seen from two different angles. Let's run the entire pipeline once end to end. The network outputs logits, 2, 1, minus 1. Softmax turns them into probabilities, 71, 26, and 3%. The true answer is cat, so we grab the probability of cat, 0.71. That is the likelihood. Take its log. Flip the sign. That gives the negative log likelihood, about 0.34. And for classification, that is the cross-entropy loss. Then backpropagation nudges every weight just a little, so that next time, cat gets an even higher probability. Do that millions of times and the model learns. And this isn't just theory, it is running everywhere. When ChatGPT reads, "The capital of France is," it predicts the next word. It might give Paris 70%. The training answer is Paris, so the loss is minus the log of 0.7. Training pushes Paris higher, maybe to 95%, and the loss shrinks. That single idea, repeated over trillions of words, is how the model learns language. Image classifiers use the exact same loss. And in classical statistics, maximum likelihood is how we fit almost every model, from linear regression to logistic regression. One idea showing up everywhere. So here's the whole story in one breath. Logits become probabilities through softmax. The probability of the true answer is the likelihood. Maximum likelihood means making the truth probable. We take the log so multiplication becomes addition, and we flip the sign so maximizing becomes minimizing. That negative log likelihood for classification is exactly cross-entropy. Probability reasons forward, likelihood reasons backward. And that one elegant idea is quietly training almost every model in modern machine learning. Thanks for watching. If this made cross-entropy finally click, subscribe to The Lost Landscape for a new explainer every week, and I'll see you in the next one.